In this chapter, we study the three-dimensional container and truck loading problem. The goal is to pack cargo items in 3 dimensions so that we use space efficiently while keeping the load safe and practical to handle. This is not only a volume problem. Real operations require stability, weight balance, and access. A plan that looks dense on paper can fail in practice if it creates unsafe center of gravity shift or blocks items that must be unloaded earlier. Our scenario is grounded in the Port of Rotterdam, which processes over 15 million 20-foot equivalent units annually. In this setting, packing decisions repeat at very large scale. We consider a logistics company that must pack 200 product types, each with its own dimensions, weight, and fragility rules. Some items cannot be placed upside down, some require temperature zones, and some must remain accessible for mid-journey unloading, which adds a sequencing layer to the packing decision. Three-dimensional loading is difficult because multiple objectives compete. You want high space utilization, but you also need a stable load that respects stacking limits and weight capacity. The chapter highlights that even a 5% utilization improvement can save millions in shipping costs annually and reduce environmental impact through fewer trips. That is why organizations invest in rigorous models, fast heuristics, and advanced algorithms. This chapter uses a tiered toolkit. Tier 1 builds a mixed integer programming model with full 3-dimensional feasibility constraints. Tier 2 uses the bottom-left fill constructive heuristic. Tier 3 uses anti-colony optimization to search the solution space through probabilistic construction. Tier 4 adds machine learning via clustering and strategy selection. Tier 5 introduces a digital twin for real-time adaptive packing. Tiers 9 and 11 then explore frontier ideas in quantum optimization and programmable matter. Tier 1 models the problem at full resolution. The model assigns each item to a container, selects its orientation, and chooses its placement coordinates. The core requirement is feasibility. Items must not overlap, must remain inside the container boundaries, and must respect weight limits. A secondary goal is center of gravity control, which matters for safety and handling efficiency. This slide defines the sets and indices. We index the items that must be packed, the available bins or containers, and the feasible orientations for each item. Operationally, orientation is critical because many products can be rotated, but not all rotations are allowed. The set of orientations captures those practical constraints and prevents the model from using unrealistic placements. This slide lists the parameters. For each item and each orientation, we define length, width, and height. For each bin, we define container dimensions. We also include item weights and bin weight capacities because a packing plan that fits geometrically can still be infeasible if it exceeds axle limits or creates unsafe loading. The big constant supports conditional constraints used in overlap and boundary logic. The decision variables represent the actual plan. Binary assignment variables select the bin and orientation for each item, and a binary variable indicates whether a bin is used. Continuous variables place each item by giving its 3-dimensional coordinates. Additional binary precedence variables encode relative ordering between 2 items along each dimension, which is what enables a clean, non-overlap formulation. The objective function has 2 parts. First, it minimizes the number of bins used, which aligns with reducing container count and transport cost. Second, it adds a weighted penalty for center of gravity deviation. This term pushes the model to choose placements that keep the load balanced, reducing tip risk and improving handling stability. The item assignment constraint ensures every item is packed exactly once. In operational terms, this prevents missing cargo and prevents duplicating an item across multiple containers. This constraint is the foundation for feasibility. Without it, the model could avoid difficult items by simply not packing them, which is not acceptable in real shipping. These constraints connect assignments to used bins and weight capacity. The activation rule says that if an item is assigned to a bin, that bin must be marked as used. The weight constraint then ensures that the sum of item weights assigned to a bin stays within the bin capacity. This avoids overloaded containers and supports safe handling and compliance. The non-overlapping constraints prevent any two items from occupying the same space. The model uses a big M formulation combined with precedence variables. Operationally, this encodes a simple idea. For two items in the same bin, at least one of them must be entirely to the left or right, in front or behind, or below or above the other. This replaces geometric collision checks with algebraic feasibility logic. The precedence completeness constraint enforces that for each item pair, at least one precedence relationship holds. This closes a loophole where the overlap logic would otherwise be inactive. In practice, it guarantees that the model chooses a valid spatial ordering between any two items that share a bin, so that overlap prevention is enforced consistently. Boundary constraints ensure that every item remains inside the container. The coordinate plus the oriented dimension must not exceed the bin dimension. This matters operationally because even a small boundary violation is unacceptable. It can prevent doors from closing, violate safety clearances, or create damage risk during loading. This visualization ties the model to an intuitive, physical picture. A good packing plan is compact, stable, and still feasible for handling. Even when the model is solved optimally, you would still validate the outcome visually and operationally because real cargo includes fragility and accessibility constraints that may not be fully captured unless explicitly modeled. The chapter provides a simple three-box example. The container has dimensions 10 by 8 by 6 units. Item 1 is 4 by 3 by 2. Item 2 is 3 by 3 by 3, and item 3 is 2 by 4 by 3. The example placement assigns them along the length direction at coordinates 0, 4, and 7. The reported result is full-length utilization and 66.7% volume utilization with total weight 33 kilograms. Tier 2 introduces a bottom-left fill heuristic. The heuristic places items sequentially at low, stable positions, which mimics how cargo settles under gravity. The method is constructive and practical. It uses priority scoring to decide the packing order, then tests candidate support points to find the best feasible placement under boundary, overlap, and stability checks. This workflow figure summarizes bottom-left fill. You start by sorting items by a priority rule, then generate candidate support points and test feasibility. A key operational detail is stability. When an item is placed above the floor, it must have adequate support from below. Otherwise, the packing plan may be geometrically feasible but physically unstable. In this part, you can see the implementation details in action. Key functions in this chunk include weighted distance score, accessibility score, evaluate location, and select facility location. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include Euclidean dist. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. The chapter includes a worked trace for the heuristic. Items are scored by volume, density, and urgency, and then sorted by priority. The reported order is item B, then item A, then item C. The reported placement matches the earlier example and yields 15.6% volume utilization and 90% length utilization, with total weight 33 kilograms. The point is that heuristics can produce reasonable solutions quickly, even when exact optimization is expensive. Tier 3 uses ant colony optimization as a meta-heuristic. Each ant builds a packing plan by choosing decisions probabilistically. Pheromone captures learned experience from previous good solutions, while heuristic information captures immediate packing qualities such as stability, compactness, and reduced wasted space. Over iterations, the algorithm balances exploration and exploitation and improves solution quality. This slide shows the probability rule used in ant colony optimization. The probability combines pheromone strength with a heuristic desirability measure. Operationally, this means ants are more likely to choose item position decisions that have historically produced good packing, but they still sometimes explore new choices. That exploration is essential because the search space is highly combinatorial and local patterns can be misleading. This figure visualizes how pheromone trails guide decisions. The algorithm is a feedback system. Better packing choices deposit stronger trails, and those trails influence future decisions. Over time, the system learns to favor stable, space-efficient placements. This is especially useful when exact optimization is too slow and when heuristic rules alone cannot capture complex interactions. In this part, you can see the implementation details in action. The key class visible here is the anti-colony facility location class. Key functions in this chunk include initializer, calculate heuristic, evaluate location, and anti-solution construction. You will notice logic related to iteration. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, the code makes the slide method executable. Key functions in this chunk include update pheromone and solve. You will notice logic related to iteration. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. The chapter reports a 10-item example using 50 ants over 100 iterations. The key metric is container utilization. The reported final utilization is 88.2%. The reported convergence trend improves from 76.2% at iteration 10 to 88.2% by iteration 100. This illustrates how pheromone-guided search can steadily improve packing quality over time. Tier 4 adds machine learning to guide packing. Instead of treating all items as interchangeable, we extract features like volume, density, aspect ratios, and fragility. Unsupervised clustering groups similar items, and then different packing strategies are applied per cluster. This reduces complexity and can capture patterns that hand-designed rules miss. This slide lists a feature vector for each item. It includes volume, density, aspect ratios, and indicators for fragility and orientation flexibility. The operational meaning is straightforward. Heavy items behave differently than light items. Elongated items behave differently than cube-like items. And fragile items impose stacking constraints. These features let learning methods recognize those differences and recommend strategies accordingly. This diagram shows how items can be grouped into clusters in a reduced feature space. The point is not the math of clustering, but the operational implication. By separating heavy small items, large items, elongated items, and regular items, you can choose tactics such as heavy bottom packing, large item first placement, vertical orientation preference, or standard bottom left fill. This improves both stability and utilization. In this part, the code makes the slide method executable. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. Key functions in this chunk include priority-based facility location. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, the code makes the slide method executable. Key functions in this chunk include Euclidean distance. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. The chapter reports clustering results for 25 items split into 4 groups. Cluster 0 is heavy and small, Cluster 1 is large, Cluster 2 is elongated, and Cluster 3 is regular. The reported performance comparison shows the benefit. Standard bottom left fill achieves 78.2% utilization, and colony optimization achieves 82.1%, and machine learning clustering reaches 85.7% with improved center of gravity control. Tier 5 introduces a digital twin. The key difference is that packing is no longer a one-time offline optimization. The twin integrates real-time data such as sensor measurements, weather, routing changes, and customer delivery priorities. As those signals change, the system can adapt the loading plan, which is crucial for multi-stop shipments and disruption-prone conditions. This architecture shows how the digital twin acts as a hub between data sources and execution systems. Inputs include sensors for weight and position, weather systems, traffic conditions, and supply chain events. The twin interacts with physical containers, vehicles, warehouse systems, and customer systems. It also supports what-if simulation so planners can test how alternative packing plans perform under different disruption scenarios. The chapter's concrete example is a cross-continental shipment from Rotterdam to Los Angeles, with stops in New York and Chicago. The reported result is a zone-based plan. Zone A uses 24% of container volume for New York deliveries, Zone B uses 35% for Chicago, and Zone C uses 41% for Los Angeles. The system reports a stability score of 0.92 against a requirement of 0.85, plus improvements such as 12.3% better fuel efficiency and 31.2% fewer damage claims. Tier 9 explores quantum computing as a future direction. The motivation is that the solution space grows extremely quickly as item count increases. Quantum approaches attempt to evaluate many configurations in parallel through superposition, which can potentially speed up the search for good configurations when classical algorithms become too slow. This slide shows the idea of a quantum state as a weighted combination of many binary configurations. Each configuration represents a candidate packing decision pattern. The operational interpretation is that instead of testing configurations one by one, quantum computation can represent many of them at once. The hard part is shaping the optimization so that good configurations gain higher probability and can be measured reliably. This slide summarizes a problem Hamiltonian conceptually. The expression combines terms that reward volume utilization and penalize violations such as overlap, boundary breaches, and instability. In practice, those terms are encoded as weighted penalties. The quality of the quantum optimization depends heavily on choosing penalty weights that enforce feasibility while still allowing meaningful exploration. This figure illustrates the circuit structure of the quantum approximate optimization approach. The circuit alternates between problem-specific transformations and mixing steps. The goal is to concentrate probability on high-quality packing configurations. While this tier is forward-looking, it is grounded in the same operational objective: dense, feasible, stable packing. Tier 11 imagines a physical cyber synthesis in which the container itself can change shape and properties. Programmable matter can reshape, adjust density, and alter rigidity to protect cargo. Operationally, this changes the problem. Instead of fitting fixed objects into a fixed box, the system co-designs the containment and support structure to maximize utilization while maintaining safety under changing transport conditions. This figure shows programmable matter transforming to create optimal packing and protection structures. The key idea is continuous adaptation. As conditions change, such as vibration, temperature swings, or changing delivery requirements, the matter can reconfigure to preserve stability and accessibility. This is the extreme end of adaptive packing. In this part, you can see the implementation details in action. You will notice logic related to iteration. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities, so you can verify that the update logic behaves as expected. In this part, the code makes the slide method executable. As you read it, focus on the sequence of steps and which variables are carried forward, because that's where most implementation bugs hide. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. To practice, start with Tier 1. Formulate a mixed integer model for a small set of boxes, and write the non-overlap constraint that separates two boxes along the x dimension. Then implement the bottom left fill heuristic and compute support percentages, utilization, and runtime complexity. Next, design an ant colony optimization approach with specified parameters and show an example pheromone update. For Tier 4, build a utilization prediction model from historical data. For Tier 5, specify a digital twin for 50 containers per day and explain how you would re-optimize when a critical shipment arrives 6 hours late. Finally, outline a quantum QUBO and a programmable matter temperature zoning design for vaccine shipment. Three-dimensional loading is a rigorous logistics problem that combines geometry, safety, and execution constraints. Tier 1 gives a complete feasibility baseline. Tiers 2 to 4 provide faster methods that trade exactness for practicality and adaptability. Tier 5 extends the scope to real-time system integration. Tiers 9 and 11 highlight frontier directions, but they still serve the same operational goal: stable, feasible, high utilization loading.